Let me ask you a question. What is the last digit of, let us say, 122 raised to 120? What is the last digit of 122 raised to 120? 122 to the power of 120. Seems like a very daunting question at first sight, right? Very huge number raised to another very huge number. There's no way you could just sit down and calculate the answer and then check what the last digit would be. If you're not familiar with modular arithmetic and modular exponentiation, it might be hard to even think of how do you start solving such a question. So by the end of this video, you'll not only know how to solve such a kind of questions, but you'll also know how to solve them quickly. So first of all, what is modular arithmetic? We look at an object every day that works on the principles of modular arithmetic. Can you guess what it is? If you said clock, you're correct. When you look at a clock, it only goes from 1 to 12. Even though in a day we have 24 hours. But whenever someone says that it's 14 o'clock, you instantly know that he's talking about it's 2 o'clock in the afternoon or 2 p.m. How did you know that? You know that the clock works on the principle of modulo 12. So modulo 12. So what we do is whenever we go past 12, we know that we have to circle back. So we get back to 1. So we know that when we have 12, we can also call it 0. So therefore, uh, even in 24-hour time, we know that 0 hours is midnight 12 a.m. And whenever we reach 13, we know that we have reached 12 once and then we have circled back and we have gone one more ahead, one more unit ahead, and we have reached 1. So 13 is nothing but 1 p.m. So modular arithmetic is just going in circles around a specific value for the mod. So for a clock, it's mod 12, but you can have any value over here. So if I ask you what is 7 mod 5, you know that what we are essentially asking is that if we had a circle, let's say here, which only had uh, 5 units, and if I moved ahead on that circle 7 times, so 4, 5, 6, and 7. So we have 0, 1, 2, 3, and 4. So this can be either 5 or this can be either 0. So if we move ahead 7 times starting at 0, where would we land? So even though we moved 7 steps, we will land at 2. We will land at 2. 7 mod 5 is equal to 2. And when learning about modular arithmetic, there is one more nuance to the notation that a lot of times instead of seeing the equal to sign, you would see the congruent sign, 3 lines instead of 2. So we would write this as 2 is congruent to 7 mod 5. And why is that so? Because it's not only 2 that is congruent to 7 mod 5, right? You can have 2 also congruent to, instead of 7, let us say we have over here 12 mod 5. So 12 mod 5 is also 2, because if you moved 12 steps, so 8, 9, 10, 11, 12, again you're at the position 2. So instead of writing equal to, we will use the congruent notation. So we will say 2 is congruent to 12 mod 5. So now that we know what modular arithmetic is, you'll soon see why it is so helpful. But first, let us learn about some properties of modular arithmetic that would be really helpful when actually solving questions using modular arithmetic. So if you have A plus B mod C, you can also distribute this mod inside and you can write A mod C plus B mod C whole mod C. And similarly, you can also have it for multiplication. So if you have A mod B, A into B mod C. So if you have A into B mod C, you can similarly have A mod C into B mod C whole mod C. So these two properties are very important because if you know that these two properties are true, you can simplify a lot of problems going forward. So how does knowing this help us solve problems such as this? Let us try to see. So once you know that 122 raised to 120 is nothing but 122 into 122 into 122 120 times, you know that it's nothing but just repeated multiplication, right? And if you look at the question, what we are asked is not the actual value of 122 mod 120, sorry, 122 to the power of 120, but we are asked what is the last digit of 122 to the power of 120. And to get the last digit of any number, what do? We can divide that number by 10 and check what the remainder is. So if we have a number 1297, if you divide this number by 10 and check what the remainder is, so divide this by 10 and you will know that the remainder is 129 and you will get 7 as the remainder. So this is the remainder. So this so dividing any number by 10 and looking at the remainder gives you the last digit of that number. This is just something particular you might have even noticed as a child studying math, since dividing it, since all the numbers other than what is in the units place are either tens, hundreds, thousands, so they will always completely divide by 10 and only leave you with the units place. And when we saw the modular arithmetic, you might have also noticed that it is also very similar to asking what the remainder is. Let's look at this again. When we ask 7 mod 5 is congruent to 2, you can also say that when 7 is divided by 5, what is the remainder? So 2 is the remainder. When 12 is divided by 5, what is the remainder? 2 is the remainder. Because as you can see, when we are walking on a circle, let us say mod 4 with 0, 1, 2, 3, you can imagine all the numbers lying on this and going in circles. So if we have 0 here, 1 here, 2 here, 3 here, then again 4 here. After 4 steps, you can see that we reach the starting place again. Because that's obvious. Since we are on a circle mod 4, after every 4 steps, we will reach the first position again. But any number of other steps, and we will be at either this position, or this position. So that means, so if we have a number, let us say 17, we know that the lowest multiple of 4 below this number, which is 16. So when going around this circle 16 times, we will just reach this starting position. And we only go one step ahead at to reach over here the 1 position. So we can just divide 17 by 4 and then look at what the remainder is. So 17 divided by 4 gives you a remainder. So you write the modulus operation like a percentage. So you have 17 modulus 4, it gives you 1. Because when you walk around the circle with 4 units 17 times, after walking 16 times or any number of times that is a multiple of 4, you will just reach the original position again. So now knowing this, we can go ahead and try to solve the problem. So we have 122 raised to 120. Since we want to know what the last digit of this is, we'll take mod 10 because mod 10 will give us the last digit. And now let's look at this property again. As I told you, the properties will come in handy a lot during solving the questions. So if you look at this property again, you know that when there are two numbers multiplied and then taken the mod at whole, you can distribute that mod inside to each of the individual multiplications. So that means we can have 122 mod 10 into 122 mod 10 and so on. So taking the mod 10 for each of them, we know 122 mod 10 is just the last digit, so we know that it's 2. So this essentially reduces to 2 into 2 into 2. How many times? 120 times. So that means we can also write this as 2 raised to 120 mod 10. So just by knowing this one property, we have already simplified this a lot. But let's use some more properties. Everyone knows the property that we have x raised to y whole raised to z equals to x raised to y into z. So using that property, we can break this into 2 raised to 2 whole raised to 60 mod 10. Correct? Because 60 into 2 would give us 120. So we just brought 2 inside a bracket and then we get this as 4 raised to 60. And we can do this again. So what we'll get? We'll get 4 squared raised to 30. So what is 4 squared? 16. So we have 16 raised to 30 mod 10. And again, using the mod property, we'll just take the units digit. So we have 6 raised to 30 mod 10. Let's take 6 square again. So we have 36 raised to 15 mod 10. And since it is mod 10, again, we can take 6 raised to 15 mod 10. As you can already see from a problem like 122 raised to 120, which is all not almost, which is certainly not calculatable by hand, we can reach a much simpler problem of 16 raised to 6 raised to 15 mod 10. And even though you can, given enough time, calculate what 6 raised to 15 is, there are much faster ways of doing that. So one way to solve this is you can first take 6 raised to 1, which you know is 6 mod 10. So, sorry, mod 10 was here as well. So then you take, just double it. So you take 6 squared mod 10, which would be 6 raised to 1 into 6 raised to 1, right? So it would be 6 into 6 mod 10, which we know is 36 mod 10, which 36 mod 10 is just 6 again. Correct? Then you have 6 raised to 4 mod 10, which is again 6 raised to 2 into 6 raised to 2, Mod 10 always. I'm not writing mod 10 again and again for the sake of simplicity, but just remember that everything we are doing is mod 10. So since we know that 6 raised to 2 mod 10 is 6, we can just do 6 into 6. So this simplifies to 6 into 6, which again gives us 36 mod 10, which again gives you 6. Similarly, for 6 raised to 8, you have mod 10. Now, again, you could do it the previous way. You could take 6 raised to 4 into 6 raised to 4, which you know is 6. Then you do 6, 6, 36, again get to 6. But now that you know that we are always getting 6, we have a cycle. Because since we have 6 and then after we double it, we are always again multiplying 6 by 6 and we are again getting 6. We know that 6 raised to 8 is also 6. Mod 10 is also 6, and then 6 raised to 8 to the 16. Mod 10 is also nothing but 6. So now that we know that 6 raised to 10 mod 10 is 6, what we actually want to find is 6 raised to 15. But we got to 6 raised to 16, which was unnecessary. But anyway, just for the sake of example, now to find 6 raised to 15, you could just take 6 raised to 8 plus 6 raised to 4, which gives you 6 raised to 12, plus 6 raised to 2, which gives you 6 raised to 14, plus, sorry, not plus, but multiplication, 6 raised to 1. So this would give you 6 raised to 15, and that we know, and we take mod 10 everywhere. So mod 10 is over here as well. Don't forget that. So again, we know that this is 6, this is also 6, this is also 6, and this is also 6. So this would be 6 into 6, 36, 6 into 6, 36. So 36 into 36 mod 10. And again, you could just multiply them. It is not that hard of a multiplication. You could just do 36 into 36. You'll get 6 6 are 36, 6 3 are 18, 21. Then you add a 0. Then you have again 18, 9, and 10. You can get 6, 9, 2, 1, and then just take mod 10 of the last digit and get 6. But again, whenever you have whenever you're using mod, always remember to use these properties. So you know that 36 into 36 mod 10 is also just 36 mod 10 into 36 mod 10, which is just 6 into 6 mod 10. So there is also a whole mod 10 over here. So this whole mod 10 gets us 36 mod 10, and finally you get 6 as the answer. So this since we were explaining this, it took a lot of time, but as you know, when you know these properties, you can just quickly take the last digits and do these calculations, find a cycle, and quickly find the answer to be 6. And just to verify this, what we are going to do is let's use some programming. Let's open Python and let's actually check what 122 raised to 120 is. So this is the actual number, and as you can see, 6 is the last digit. Now this is not it. There are a lot of other fun tactics that modular arithmetic allows you to do. One of them being using negative numbers. So let me ask you another question. What is the last digit of 9 raised to 1, 2, 7, 4, 5? Now looking at this, this is completely unsolvable by hand. You cannot calculate such a large exponent. And even trying to break this down using techniques like this, where we took the squares in and made this number bigger and made this number smaller, This also seems very far-fetched in this question. But since it is asking what the last digit of this is, we can use a clever trick. So what we actually have to find that now you know by now you know that we have what we actually have to find is 9 raised to 1745 mod 10. And for mod 10, one more thing that we did not mention while looking at the congruent notation is when I say that minus 1 is congruent to 9 mod 10. This is also a correct statement. Coming back to the circle, if we say that 7 mod 5 is 2, or maybe let's say 3 mod 5 is congruent to minus 2, that is correct, since if you are in a circle with 5 units divided into 5 units and you have to land at the position minus 2. So minus 2 is 2, but in the right direction, 2 steps in the right direction. You can see we landed at 3. So I'll just redraw the circle as it has become very cluttered. So this is 0, 1, 2, 3, 4. So starting at 0, if you go in minus 2 steps, so 2 steps but in the opposite direction, you are still landing at 3. So using this logic over here, we can write that 9 mod 10 is also equal to minus 1. So we have minus 1 raised to 127.45 mod 10. And now that we know that minus 1 raised to an even number will give us plus 1 and raised to an odd number will give us minus 1. So this, since 5 is the last digit, is the odd number, we again get minus 1. So minus 1 mod 10. And to convert this to a actual in since minus 1 cannot be the last digit of a number, we convert it back to a positive number and say the answer is 9. So actually this number is way too big to even calculate in Python. But if we even had 9 raised to 127, which is also a very big number with a odd number over here, we will still find that 9 is the last digit. And to verify that, let's just check this. So we have 9 raised to 127, and you can see 9 is the last digit in fact. So even a question as daunting as this can be solved without any calculation if you use the modular arithmetic operations smartly. Now, one more question, not very related to modular arithmetic, but similar. If there is anything specifically mod 9, so if you have 1, 2, 3, 4, 5 mod 9, so you know that anything mod 9 is just dividing this number by this and finding the remainder. But when you have a number so big, you can go with the traditional method of dividing a number. But a much faster way for 9 is counting the sum of the digits. So for example, if the question was, what is the remainder when 1, 2, 3, 4, 5 or 12,345 is divided by 9? So you know they are asking 1, 2, 3, 4, 5 mod 9. What is 1, 2, 3, 4, 5 mod 9? It is the remainder when this is divided by 9. And to find that, the clever trick for special case 9 is that you add all the digits. So you have 1 plus 2 plus 3 plus 4 plus 5, which is equal to 3 plus 3, 6, 10 and 15. You add the digits again. So you have 1 plus 5 and you get 6. So 6 is the remainder. because the divisibility check rule for 9 is that if all these sum of digits add up to 0, or they add up to a 9 or a multiple of 9, that mean sorry, they cannot add up to 0. But if they add up to 9 or a multiple of 9, this is the whole number is divisible by 9. But they forget to tell you that the number that you get over here is actually the remainder. So the rule holds true, right? If you get 9 or 18, a number which is a multiple of 9, if that number is the remainder, then you can obviously still divide that by 9, right? So that number is completely divisible by 9. But since we got 6, this is not divisible by 9, but 6 is the remainder. So again, let's go to our Python shell just to check our answer. So we have 1, 2, 3, 4, 5, and so in programming to get a mod, you use this percentage sign, and you can see the answer is indeed 6. So before ending this video, just let's just look at one last question. 7 raised to 2 to 2. So when this number is divided by 2 to 3, what is the remainder that we get? The remainder. Now, again, the question is pretty straightforward since it's asking for the remainder. What it is asking is, what is 7 to 2 mod 2 to 3, right? So solving this seems pretty daunting even by the methods that we have learned till now. You can obviously just take 7 square, then you get 49, then take 49 square, you get some number which is bigger than 2 to 3, then you take the 2 to 3's mod, and then you get back to a number which is smaller, and then keep on repeating till you find the cycle. So maybe the mod of 7, so maybe 7th mod 23 might have some cycle like 2, 4, 5, 35, 37, then again 2, then you get to know that okay, this is repeating 3, 4, 5, 6 every 6 times. So you divide this by 6 and blah, 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 blah. Too long. You can't keep on doing that in your exam. So for that, there's a simple solution which directly gives you the answer and says that 7 to the power of 2 to 2 is congruent to 1 mod 2 to 3. And therefore the answer is 1. Let's just verify it. So you have 7 raised to 2 to 2. Let's take this in a bracket. And you are getting mod 2 to 3. And the answer is indeed 1. And how did we know this? The answer is Fermat's little theorem. So what Fermat's little theorem is, we'll cover in the next video, as this video has already been a bit on the longer side. But we'll see how you can use this theorem, this little theorem, to directly look at questions like this and say that the answer would be 1. So again, thanks for watching. See you in the next one.